In this session I want to show you how it's possible to rewrite this group table for D4, the dihedral group of a polygon of 4 equal sides, a square in other words. Now here you have eight elements, 4 of type rotation, 4 of type flip. That's where the hedral comes from. Okay. So the researchers, quite a while back, I guess I'm I'm a bit weak on the history of this subject. I should study this more. Anyway, I don't know who actually discovered this stuff, but somebody discovered that you could rewrite the dihedral group in terms using only 2 generators. And as I said towards the end of the previous session, those 2 generators are now we're talking about context of symmetry operations of the square, right? So D4. So R here is a rotation anti-clockwise by 90 degrees, right? It's that operation. So that's one of your generators. And the second one, it doesn't really matter which one you choose, but it could be any one of the 4 flip operations, flip symmetry operations. So it could be about the horizontal axis, could be about, what did I say L was? Can't remember, was it that way or that way? M, the other diagonal, and V, the vertical flip. So it doesn't really matter which one of these 4 you choose. You'll get the same. You get an isomorphic group, and I'll prove that. I'll show you that that's true to some extent. All right. Now, instead of using like R and H or R and L or R and M or R and V, that's a bit tedious since they're all these 2 generators generate these pairs like R and H or R and L, etc. They generate isomorphic groups. So let's just relabel this one little a. Okay, so that's your first generator, and whichever one of these 4 you choose, just call it B. Right? Now, in the context of D4, a to the 4th, in other words, you rotate 90 degrees 4 times. Of course, you'll get E, right? You get back to where you started with. 490s is 360, which is a full rotation. So a to the 4th is E, right? Now a flip operation, if you do it twice, you get back to where you started with. So B squared, B done twice is E. So a to the 4th equals B squared is E, right? Now that's a kind of relation between A and B, right? You know that a to the 4th equals b squared. So there's some kind of connection or relation between a and b. So the fact that a to the 4th is e and b squared is e, they are 2 relations as they're called. Now I'll be talking a bit more about relations. Now, if you look at this group table, oh, by the way, use this group table, right? Do not use the group table in the textbook. It has errors. It is, let's see what page. On page 127 of your textbook, I found 16 positions of the 64 entries in the table. I found them to be wrong. So use this one, right? Now, I created this table, and at first I was a bit surprised when I started to get differences between what I was getting and what was in the textbook. Now, to generate this table, I recommend you cut a little piece of paper, and on both sides, this side and the other side, I've written A. And I've got a D here and a D on the opposite side. If I turn it around, So D here, and similarly B on this corner and C. Now using this little piece of paper, you can flip and rotate round diagonals and whatever, and you can generate this group table. So use this one. Don't use the textbooks one, because there are errors. I guess the author didn't check carefully enough the detailed nitty-gritty of his table. Right? Okay, so using this group table, you can show that applying symmetry operation A, then B, then A, remember you start from the right, that whatever choice you make for B, that's your second generator, whether it's this one or this one or this one or this one, whichever it is you choose, you'll get A, B, A is equal to B. Let's just prove that for just one case, make it sound plausible. But I mean, you can use this group table and check that that's true for all B, all possible choices of B, namely H or L or V or M. So I don't know. Let's choose H. Okay, so this is H. So in terms of this table, the letters used here, the element labels, this would be R, H, R. Okay, and we have to show that it's equal to H. R, H, R equals H. Okay, so R, H. R, H is L. Right? And then it would be L, R. L, R, H. Okay, and similarly for the other three cases. Right? So convince yourself of that. All right. Now this is not in the text. Well, it is between the lines. So I'm spelling it out. Makes it easier to understand. Well, that's the role of a prof, right? Okay. So now the four cases. B can be any one of these four. So say you choose B equals H. I'm just going systematically through this list here. So if B is H, then BA, or actually AB, if you read from right to left, but if I'm reading just ordinary English method, so BA, it'll come out as M, and you can check that from the table, right? And BA squared comes out as V, and BA cubed comes out as L. So in other words, using B and A, your two generators, remember, you're generating the elements. Now with A, you can generate all rotations, right? A is 90 degrees, A squared is 180 degrees, A cubed is 270 degrees, and A to the fourth is E, right? A to the fourth is E. So with A, you can generate half of your table. And if you choose B as H, you can, with B and A, you can generate the four flip operations here. They're all there, right? All four of them. Now, a similar story if you choose B as M. So, just B as M. So B and BA, using this table, BA is V and BA squared is L and BA cubed is H. So again, all four of them are there, right? You've generated all four of the flip operations. And similar story for the other two. You can check it out if you want all the details, right? So the point is, this is the point. With A and B as generators, you can generate all elements of D4, and there's the proof, right? If you choose B, you get all four. If you choose N, you get all four. Choose V, you get all four. You choose L, you get all four. Okay, so therefore, these two elements, A and B, generate D4, this group. So that allows you to rewrite the group table. Okay. Now it doesn't matter which one of these four it is. So if you chose B to be H, so you'd have H here, right? So you have H here, and you'd have a corresponding. What would be A? Well, then you'd have M. So if you chose B equals H, you'd have HMVL, HMVL here, and HMVL here. Okay. Now, and if you chose M, well, you get the corresponding 4 here and 4 here. And you get a group table that's isomorphic in the 4 cases. So it doesn't really matter which one of these 4 you use. Okay? So let's just call it B. All right? So your four flip operations are generated by B and B and A. Okay? So there are your 4 operations in terms of your 2 generators A and B. There are your 4 operations. Okay? Now you know you've got relations. A B A is B. You know that, right? You proved that readily. We did it just in one case, but you can do it for all 4. So you've got this and this relations. So sort of connections, formula involving A and B. So these sort of things are called relations. Now using them, you can actually generate the values in the group table. Now once you get to that stage, it becomes algebra, right? You sort of forget about group theory and whatever for a while. It just becomes algebra. So you use the relations, use these to fill in this group table. So it just becomes algebra. And using these relations, you can write these terms, the results of binary operations, one of these binary operator with one of these, and you can, by doing a bit of algebra, you can write all of these in the following form, either like this, just with A's and E, or like this with the B on the left, right? So you've got B, BA, BA squared, BA cubed. Now how to do that? For example, let's find what's the result of the binary operation AB. So A, B. Okay. So you've got here BA cubed. Well, where did that come from? Because it should be like AB, right? Well, putting the A on the left. So I'm just calling it AB, in the usual left to right English way. So AB. So how do you prove that AB equals BA cubed? Why have I written it this way? Well, so how do you show that AB equals BA cubed? And similarly, let's say BA. Where is it here? Oh, that's okay. B. Alright. Well, how do you show that? Right? Well, if you post multiply here by A to the 4th, you're just multiplying by the unit, not changing anything. Okay? So this is just equal to that. And you may say, well, why do you do that? Well, you'll see in a minute. You can rewrite this as this. Okay? So you split this up into A and A cubed. And why did you do that? Because you know that, because one of the relations, this one, you know that, where am I? You know that ABA is B. Okay? So you just replace that with B. So you get BA cubed. So AB is BA cubed. A, B here, BA cubed. Right? There it is. Okay?